Welcome and thank you for joining us. My name is Shervin Shaku, and along with my colleague Hugo Castro, we will be presenting today's ETAP webinar titled To Shed or Not to Shed, a proactive intelligent load shedding solution for industrial systems. In this part of our load shedding webinar series, we will discuss the need for an intelligent model-driven load shedding solution and share a user case study for a cement manufacturing plant from implementation to benefit recognition using ETAP iLS Intelligent Load Shedding System in action. ETAP iLS is a model-driven controller integrated with real-time operational digital twins to validate, optimize, predict, and perform load shedding for industrial systems. ETAP also offers a dedicated purpose load shedding and management solution as ETAP DILS or Distribution Intelligent Load Shedding that provides load curtailment, optimal distribution feeder load preservation, and demand-side management for electrical distribution networks. The objective of load shedding is to preserve critical process by saving essential loads and protect against production loss, maintain service continuity, system uptime, and process survivability, while minimizing the number of loads to be shed due to a disturbance in order to reduce and/or eliminate process interruptions, all with an overall objective to lower the cost of operations. But more to this, load shedding is a critical strategy to ensure power system stability requirements and constraints are met, such as critical clearing times and critical islanding times to maintain system stability and nominal frequency. Fast response to network dynamics, that is, longer the response time to shed after a disturbance, the more loads are needed to be shed to save and recover the collapsing system magnetic energy due to the rapid dissipation of magnetization in electrical machines. This strategy should provide answers to questions such as, are the predetermined spinning reserve policies too costly, and how to reduce cost of spinning reserve equipment and fuel cost. It is vital to know and understand how the design load shedding logic and scheme will perform under actual operating scenarios. The ability to easily simulate what-ifs, test and confirm load shedding system response, both offline and in real-time operation mode, is at the core of a reliable and repeatable load shedding strategy. Load management and orderly restoration is the ability to recover quickly and restore effectively to minimize the duration of a costly downtime following a disturbance, ensuring faster process startup and alignment. As an example, to restart a large electrical load in a copper mine, such as a copper floating concentrator, it will take 30 minutes or longer, and each minute of downtime causes a production loss of tens of thousands of dollars. Electrical systems are subjected to disturbance of various magnitude at various locations. These disturbances can cause interruption in production that have substantial impact on revenues in range of millions of dollars per incident. Incorrect response to a disturbance can cause system instability, equipment damage, or even total plant shutdown, resulting in lengthy process disruption, loss of revenues due to inadequate or overly conservative load shedding actions, safety issues, costly recoveries, and fines, all at the owner-operator's expense. But not all load shedding systems are equal. This chart represents response time from slow to fast versus action type from reactive to proactive. At the top, we have breaker interlock load shedding. This is the simplest brute force method of carrying out load shedding. For this scheme, the circuit breaker interdependencies are arranged to operate based on hardwired trip signals from an intertie circuit breaker or a generator trip. This method is often used when the speed of load shedding is critical. Even though the execution of this scheme is fast, the breaker interlock load shedding always results in excessive and unnecessary load shedding. Under-frequency load shedding is often considered conventional and backup scheme. It considers fixed load reduction at fixed system frequency level. This scheme is inherently slow to respond due to the time it takes for the frequency to reach the predefined setting, plus the intentional time delay to prevent nuisance tripping during frequency spikes. The setting of each frequency relay is usually determined based on the most severe disturbance conditions and most conservative generation and loading levels. This means excessive load shedding for the majority of conditions that are not as severe. PLC-based system or programmable logic controller works based on the total load versus number of online generators and the detection of under-frequency conditions. At each substation, a PLC is programmed with a hard-coded logic to initiate a trip signal to feeder breakers to be shed at a preset sequence of loads. This static sequence is continued until the frequency returns to a normal and stable level. The major drawback of this scheme is the lack of system-wide knowledge and the operating conditions, as well as the slow response time, the time between the detection and the load shedding action during transient disturbances, which causes more loads to be dropped. A protection class load shedding controller offers advantages over PLC-based scheme, such as the use of a distributed network via a power management system, as well as an automated means of load relief. However, in such applications, monitoring of the power system is limited to a portion that is monitored with scattered information. This drawback is further compounded by the implementation of predefined load priority tables that are performed sequentially to curtail blocks of load regardless of dynamics changes in the system, loading, generation, or operating configuration. The system-wide operating condition is often missing from the decision-making process, resulting in insufficient or excessive load shedding. All these schemes have inherent limitations. They lack operating knowledge of the complete system, with no digital model since they use hard-coded logic, and they only offer best guess or trial and error method with no adequate validation means to simulate and test load shedding system response. They result in excessive or insufficient load shedding with no detailed understanding of dynamic system response, and they are difficult and costly to upgrade and configure, requiring additional coding and programming as the system changes and grows. A proactive intelligent load shedding system provides faster and proven optimal load relief by utilizing an electrical digital twin foundation with embedded power and process predictive analytics, adaptive optimization algorithms, action validation based on actual operating condition, and knowledge of past system disturbances. This model-driven solution provides power system topology to automatically analyze and track the system changes with fast-acting response to triggers. Optimal load shedding is performed using the correct and optimal amount of load to be shed depending on the system dynamics, inertia, and actual operating condition, as well as the disturbance types and duration of the disruptions. Using ETAP's digital twin model and software-in-the-loop technologies, load shedding scenarios are designed and tested using proven engine and predictive analysis, such as transient stability analysis to recognize different system patterns in order to predict system response for different disturbances. This allows for verification and validation of load shedding logics and the system predictive behavior via simulation prior to field deployment. With embedded system analysis, predictive analytics, optimization algorithms, logic and action validations, ETAP iLS offers a comprehensive load shedding design and real-time operation monitoring. The iLS controller uses the operational digital twin with real-time operating data and dynamic load priority tables to predict the best load shedding scenario in anticipation of disturbances. At the onset of receiving a disturbance, ETAP iLS controller located at the substation executes pre-calculated actions to instantaneously trip the optimal number of loads to ensure system stability and maintain service continuity. In the past 20 years since the first ETAP iLS installation, our clients have significantly benefited from this patented technology to ensure safe and reliable operation across a wide range of industries. Today we would like to share with you one of our success stories for Lafarge Holcim cement plant. ETAP iLS was installed at Holcim plant in El Salvador in mid-2015. Since the deployment of ETAP iLS, the plan has gained immediate return on investment of over $2 million in ongoing saving and outage avoidance costs, with 95% reduction in unplanned outages. The case study will first highlight the changes faced by Holcim operations due to system disturbances and the impact to the process. We will then demonstrate and discuss the justification and the key drivers for replacing the existing Siemens PLC-based load shedding controllers with ETAP intelligent load shedding system and the realized benefits to Lafarge Holcim.
Lafarge Holcim system runs off a 32 megawatt diesel generation plant. This plant provides power to Holcim's two process units as well as it sells power to the utility when the demand of El Salvador's national grid requires it. The connection to the utility grid is a 25-kilometer line to Guajoyo Hydroelectric Plant substation. The kiln load is the most critical process unit for the operation due to the long restoration time required to bring this unit back online after it trips. Under certain conditions, the plant operates in a landed mode, where both process units are fed from the in-plant diesel generators. In other scenarios, the plant splits into multiple subsystems where critical processes, located in Maya unit, are fed by the DGs, and the rest of the loads in Ronco process unit are fed from the utility grid. The main production process starts at the reception of the lime stock material. From there, the rock is crushed, mixed with other aggregates, and heated in the main kiln. Then it's cooled and finally grinded, ready for packaging and storage and delivery. All process components are important to production. Failures in any stage of the production will cause losses and delays, not to mention the complications associated with restarting and reheating the kiln unit, which takes at least 2 hours to restore back to operation. Given the tropical nature of El Salvador's weather, the Holcim plant suffers adverse weather conditions, causing the power supply from the utility grid to be unreliable. The grid averages more than 20 outages per month. Most of the grid outages resulted in process interruption and plant outages. In an effort to mitigate such problems, Holcim implemented a PLC-based load shedding system from Siemens. The solution turned out to have many shortcomings given that it did not have the digital twin model to understand system dynamics or connectivity that the plant required due to the modes of operation. The PLC-based load shedding system shortcomings drove Holcim to find a more intelligent solution that will address the following main concerns. 1. Reduce the outages due to utility grid disconnection. Holcim plant was suffering from overshedding after grid disconnection, which caused process and plant shutdowns. Primarily, the kiln was being tripped, resulting in a 2 to 3 hours of production loss. 2. Operations in unlanded mode. To avoid disruptions due to utility grid disturbances, often the plant was operated in unlanded mode. The load shedding system needed to adapt to the new condition. The load shedding system was failing to load shed fast enough, failing to keep the plant in operation when a generator failure occurred. 3. Management of multiple subsystems. Another common mode of operation was to operate the plant in multiple subsystems. Without a digital twin model, the PLC-based load shedding did not have the intelligence to identify the load subsystems. The location of the load with respect to the disturbance was unknown, causing load shed in the wrong process units. Under this situation, not enough load was shed in one unit, causing process interruptions. In the other subsystem, there was unnecessary disruption to the process. And 4. Ability to test and validate load shedding scheme. Validating the load shedding scheme from design stage to operation is very important. The PLC-based solution lacked an integrated tool to validate dynamically the response of the electrical network. These allow for an implementation of a load shedding with hidden shortcomings. It failed to protect the electrical network from instability during transient disturbances under all modes of operation. At Holcim, due to the lack of utility reliability, it was very important that the system survive continuous disconnections from the grid. Periodic unplanned process shutdowns occur almost every time the utility disconnected. The main issue was that the PLC-based load shed system from Siemens was determining what to shed from a static load priority table. In most cases, it was overshedding, causing overfrequency in the system, resulting in the kiln to trip and often escalating to plant shutdowns. The iLS load shed optimization solved the kiln tripping and plant outages. iLS runs continuously, predicting the required load shed for all disturbances, including grid islanding. It calculates the available spinning reserve based on operating parameters, electrical and non-electrical data. Armed with this information, iLS then selects the optimal combination of loads to be shed that closely matches the predicted required load shedding. This minimizes the disturbance to the process. iLS uses the initial load priority tables to dynamically generate optimal load priority tables for each disturbance and subsystem. It then arms the controller for instantaneous response when disturbances in the electrical network are detected. The existing PLC-based load shed system used sequential static load priority tables, resulting in 45 to 88% over the actual required load shedding. In comparison, ETAP iLS optimal load shedding matched the required load curtailment with a maximum deviation of 3%, which is negligible when considering contingency in the spinning reserve. The optimal load shedding was the solution to prevent overshedding at the plant. It eliminated the kiln shutdowns and plant outages due to overfrequency. More importantly, it is helping Holcim save over $750,000 in production loss avoidance per year. In other productions, such as metals and mining, the annual realized savings have exceeded $5 million. During the severe weather conditions, Holcim performs plant islanding from the grid. In the past, an extra diesel generator was required as a hot standby unit for redundancy in case of a trip, at the cost of additional fuel consumption to keep the unit running. This resulting in reduction of capacity of available spinning reserve, making the system more susceptible to shutdown due to disturbance in the plant. Under this condition, a single failure or missed operation of a generator will cause a complete blackout. Now let's see how to visualize this condition in iLS. When the plant is interconnected, there is no need to shed if a generator trips. When the system is operating in island, iLS predicts generator response and determines the spin reserve and how much to shed. Loads are dynamically selected and armed at the controller, ready to be shed instantaneously upon a disturbance trigger received by the controller. The PLC-based controller system is reactive. That is, it did not respond fast enough to the changes in the spinning reserve and ignored the system dynamics, hence miscalculated the required number of loads to be shed. The ETAP iLS controller, using the digital twin model with dynamic data and topology, proactively identified the islanding mode and predicted the spinning reserve under the new condition. The benefits that iLS has brought to the operation of the Holcim plant in islanding mode are summarized as follows. Reduction of fuel costs is the first direct savings. Holcim does not need to operate with hot standby generator when the load shedding system is accurate and optimal. Using the digital twin model, iLS understands the response of the generator controls, making the best decisions for selection of load to shed. Given that the system is proactive, the controller is armed for instantaneous response. Intentional delays can be added for special conditions. As a result, iLS eliminated the electrical system and process outages when operating in island mode. Another common operational strategy that Holcim utilizes to minimize utility grid disturbance impact in the plant is to island the critical process unit Maya from the utility grid and feed it from the in-plant generators. Less critical processes, El Ronco unit, including final grinding and packaging, are maintained interconnected to the grid. In this scenario, the load shedding system needs to be able to recognize multiple subsystem configurations, the location of the disturbance, and associated loads for each subsystem. iLS multiple subsystem management is an important capability to many applications over protection class and PLC-based load shedding systems. Without connectivity and digital twin model, significant hours have to be spent to determine the best guess subsystem scenarios using Boolean logic. iLS automatically tracks the system configuration, disturbances, and loads for each subsystem. It eliminates potential errors in logic and reduces testing time dramatically during implementation. In this example, we can see both process units islanded from the grid. Notice the grid disturbance Guajoyo is in subsystem 3. When a Ronco unit is islanded and interconnected to the grid, the Guajoyo disturbance, load 5 and 6, switch to the same subsystem, due to the topology change detected by iLS. ETAP iLS uses the intelligent model to track the locations of the load with respect to the disturbances. It selects the loads that belong to the subsystem where the disturbance is located. For Holcim, it means that while they operate in multiple subsystems, the disturbances in one unit will not affect the other. The result is that the utility grid disturbances in this mode only affect the packaging plant. iLS eliminated the process interruptions and downtime related to the load shedding in the run subsystem under subsystem operating mode. Validation of the load shedding system is a key factor in delivering a system that will work in all conditions of operation of any industrial system. It is also important after delivery for the customer. They will be able to determine the impact of system upgrades and operation actions in the load shed system. PLC-based and protection class load shed systems lack the validation capability. They don't have the digital twin model to validate the electrical system response to disturbances and load shed events. In any project with PLC and protection class load shed controllers, there is a costly and time-consuming process of testing using third-party solutions. It requires to model the electrical system in a third-party real-time hardware and communicate it to the load shedding controller to see the response. In systems such as oil and gas implementations, they invest hundreds of thousands of dollars to get real-time systems to test the load shed system. In ETAP iLS, it is integrated, and therefore what you are testing and validating is the same identical controller system that will be installed. iLS allows you within the same solution to go through the process of implementation and validation from design to operation. At the design stage, in iLS you can prepare the scheme logic from an automatically created logic provided by ETAP. Then simulate the disturbances in the iLS simulator. Validate the system response and transient stability. Analyze the results. Then deploy the scheme into the controller. Even if the controller is online, you can update it without bringing it offline. Once in operation, the user can simulate different conditions and system upgrades and go through the validation process. Let's see an example of transferring the iLS simulation results to transient stability. From the list of disturbances, I select one to simulate it in transient stability by right-clicking on the disturbance and selecting Simulate in TS. We will create a study case TS5, use the default study case name, trigger time, and trip delay, which is the controller operation time. We will create a new study case in ETAP. I go to ETAP and see that the study case is already there. I open the study case and see that the disturbance data, generators and utility separation, as well as the load shedding trips are there. I close the study case and run transient stability. After a few seconds, I can verify if the load shed is correct. I will open the plots and check the speed of the surviving generator. Here we can see that some swings in the speed, but also that it recovers after a few seconds. Quickly we identify that the system is stable. ETAP iLS provides an integrated solution to design a smart logic to manage single and multiple systems, perform simulation to validate the load shed schemes, and understand system dynamics. iLS validation comes with integrated transient stability analysis, offline load shedding logic schemes design, simulate and test recommendations, real-time logic validation. With this solution, integrators and end users can identify and eliminate any potential hidden conditions that will not be seen by debugging PLC control logic. By identifying shortcomings early in the implementation, the load shedding logic can be tuned to address such issues. Hundreds of thousands of dollars can be saved by not investing in costly third-party solutions to validate the load shedding system. For Holcim, in a short time, ETAP was able to validate the system performance and operation before installing the system online. In summary, iLS has brought many benefits to Holcim. Accounting for all the benefits, Holcim is saving nearly $2 million per year due to reduction of production loss. iLS eliminated the impact from utility grid disturbances and allows operations to run the plant islanded or in multiple subsystems. It reduced fuel consumption by eliminating the use of generator as a short standby unit. 95% of reduction in process shutdowns has been achieved. The system was configured, validated, and verified using its integrated validation solution. The digital twin model included the dynamic models of the generators for transient stability simulations to prove the system stability after every disturbance.
ETAP offers a turnkey load shedding solution from design to operation. The solution includes an integrated software and controller hardware combined with ETAP's expert engineering and system integration services to design, implement, and deploy ETAP iLS. Our global ETAP automation team have a vast knowledge and experience to guarantee the success of your load shedding projects. For more information on ETAP iLS, please visit etap.com/ILS and contact your regional ETAP representative for additional case studies and request a personalized presentation on how ETAP iLS makes faster than real-time decisions.